The framework of this car is going to be clamped in a special fixture. This holds the steel assembly firmly in place while it's spot welded together. On this large industrial lathe, we're turning an extremely heavy component. Here, the component is firmly held or restrained between the tailstock and the chuck. Let's see how well this component is restrained. It's a good job the lathe wasn't turning at speed. And what about this? Drilling sheet metal. Another component insufficiently restrained. Apart from being extremely dangerous, this lack of restraint can result in defective work. A grind wheel revolves at very high speed. A component that isn't restrained in this sort of situation is liable to shoot out from under the wheel. It could even cause the wheel to shatter. The restraint looks sufficient here. But no, and this time we've damaged the cutting tool. To find out how to restrain work effectively, we need to start with a component that isn't restrained at all, like this one. It's free to move this way, and this way. It's free to move in any of these three directions, each at right angles to the other. It's also free to turn about each of these three directions. Now we can prevent this component from moving down by putting it on a base plate. Any movement in this direction can be prevented by locating it between dowels. And the same goes for any movement in this direction. But there's still one direction in which it's free to move. Up. To prevent this, we can clamp it down to the base plate. Now we've prevented movement in all three directions. We say the component is positively restrained. Here we've put that method of restraint into practice. The block is held between 8 metal dowels fitted into the base plate, and these prevent movement in 2 directions. Add the clamps and the block can't move in any direction. We've mounted this component on a milling machine. Let's take a cut. In this operation, the cutting forces acting on the component are relatively small. In fact, the forces are so small that the metal dowels aren't really necessary. So let's do away with them. Now, in 2 directions, we're relying on a frictional restraint obtained from clamping forces. When machining, clamps are often used for work-holding purposes. In this case, it's a component on a drilling machine. By clamping the work to the table, we've prevented it from moving up and down. To prevent the work from spinning round, there's only the frictional restraint resulting from the clamping forces. Clamps can also be used to hold a component onto the faceplate of a lathe. When doing this, it's important to make sure that the faceplate is balanced. Can you think why? Here we're setting up to drill a hole in the component. On the lathe, drills are usually mounted in the tailstock. First, we provide a start for the drill by using a center drill. The work rotates at very high speed while the center drill is fed into it. As the work rotates, it experiences a large force which tends to make it fly out from the center. Any outward movement is prevented solely by frictional forces. Once it's been center drilled, we can machine the hole using a twist drill. In this case, a large diameter drill. Now, as well as preventing the component from flying off the faceplate, the clamping forces must also provide sufficient frictional restraint to prevent the component from moving as a result of the cutting forces. Will clamps alone be sufficient to restrain the work in this instance? Well, that's damaged the work, but what's it done to the milling cutter? No cutter grinder would be able to correct this amount of damage. Here, the work is held securely. It's restrained by metal dowels or stops, as well as clamps. The stops provide positive restraint where previously restraint was only frictional and insufficient. This component is held against an angle plate by a clamp. See what's happening? Again, the frictional restraint from the clamping forces is insufficient. Now we can prevent this from happening by resting the component on some metal packing pieces. And we clamp it in the same way as it was before. The metal packing pieces will provide positive restraint in the downward direction, the direction in which the drill feeds into the work. A vise is really a special type of clamp. This vise can be fixed in several different positions. By using it in this position, the work is positively restrained against the action of the cutting forces. The work in this shaper is restrained in a similar way. So far, we've only considered ways of holding rectangular components. What about round ones? One device that'll prevent it from rolling about is a V-block. In a V-block, a component is positively restrained from moving left and right. But it's still free to move backwards and forwards. We can prevent any movement in this direction by using a suitably designed clamp. Can you think what kind of restraints the clamp will provide? Now, we've restrained the component from moving in the V-block, but what about the V-block itself? It's only prevented from moving downwards. Well, here's one way of preventing both from moving, a magnetic V-block. As it is at the moment, it's no different to a non-magnetic one. Switch on and the magnetic forces provide the additional restraints necessary to prevent both the component and the block from moving in all three directions. Can we use these magnetic forces to restrain any material in the block? What about brass, a plastics material, or aluminium? Let's try brass. Of course, it's not a magnetic material. A V-block is often used to hold a circular component when drilling. The block and work can normally be restrained by clamping them to the machine table. Packing is needed under the other end of the clamp. It should be high enough to keep the clamp horizontal. Well, almost. Can you work out here in which directions the component is positively restrained? On a lathe, circular work can be restrained in several different ways. In this chuck, positive restraint is provided in two directions. In the third direction, along the axis of the machine, restraint is frictional. Here we're using a chuck with different jaws. This time, the jaw shape provides a positive stop behind the work. On a lathe, work can also be held between centres. Before mounting the work, each end must be centre drilled. To drive the work round, a driving dog is fitted to the headstock end of the component. This will locate in the driving plate. The centre hole at the other end is greased. Can you think why only one end? Here the work is positively restrained in all three directions. When carrying out work on a component, it's necessary to ensure that it's supported in the right places. Do you think there's anything wrong with the way this rod is restrained? Well, can you see what's happening? The downward force of the drill is causing the work to deflect. This is because the V-blocks are too far apart. A component should always be supported as near as possible to the point where the force is applied. In this case, as near the drilling point as possible. Now there's no observable deflection at the middle, but what's happening to the ends of the rod? Do you think they need supporting? Cutting forces can cause work to deflect on a lathe. This long bar is being restrained in the chuck at one end. What happens if we want to take a cut at the other end? The noise you can hear is called chatter. As the tool is fed in, cutting forces cause the work to deflect and vibrate. The result is a poor surface finish to the work. Here's one method of overcoming this. By using a dead center in the tailstock, we can support the free end of the work. That sounds better. The work is no longer deflecting, so the cutting action is much smoother. Another method of providing additional support on a lathe is to use a fixed steady. This is bolted to the bed of the lathe and has 3 jaws, each adjustable. The jaws are tipped with a low-friction material. Each one is adjusted until it just supports the work without deflecting it. You'd use a method like this if you were going to drill into the end. It's not only cutting forces that can cause work to distort. This component is supposed to be circular. Now, if we'd wished, we could have restrained the component from the inside using the same chuck, but with different jaws. This time, less clamping force is used, and the component remains circular. How would you restrain this in a vise? This time, the clamping forces have broken the component. It's cast iron. All that was necessary to prevent it from breaking was a small packing piece. Now here's something for you to think about. This is a casting which needs a lot of machining. It's a component for a drilling machine. Let's look at the finished job to see what needs doing. First, we've got to bore these 2 holes, making sure their axes are at 90 degrees to one another. Then this slot must be cut through. And finally, these 2 lugs have to be drilled and spot-faced. Can you work out how you'd restrain one of these castings for each of those operations?